Today, the words free radicals are virtually a household name, and free radical scavengers, or antioxidants, crowd the shelves of health food stores and pharmacies alike. Yet, nearly 5 decades ago, one man had the realization and determination to pursue his research and bring to the attention of the world the existence, formation, and damaging effects of free radicals. Here to explain his free radical theory of aging, it is an honor and a privilege to introduce to you Dr. Denham Harman.
First, I'd like to thank Rob Watson and the other members of the organizing committee for inviting me to participate in this conference and this magnificent location and building, and to talk on the free radical theory of aging. I'm going to say a few words about the phenomenon of aging, the origin of the free radical theory of aging, and some of its applications, including the pathogenesis of disease. Aging can be defined as a gradual accumulation of changes in the body which lead eventually to disease and death. Humans have learned how to decrease the chances so that as over time, average life expectancy at birth, which is a function of its chances of death, has gradually increased. It was reached about 30 years and 2,000 years ago in Rome. In this country, average life expectancy was about 47 years in 1900, and gradually increased, as you can see here. This is females, males, and this is the total average. Similar curves can be drawn for other developed countries. This next slide shows average life expectancies, males and females, for the whole population, 4 developed countries: United States, Switzerland, Sweden, and Japan. The thing to note is that these figures are 6 to 9 years short of the potential value of the average life expectancy at birth of about 85 years. This slide is taken from Swedish vital statistics data and a plot of the log of the chance of death for Swedish females as a function of age in various periods of time from mid-1700s up to 1992. The thing to note is that the curves have gradually decreased, and this parallels the improvements in general living conditions. That is, better nutrition, better housing, better public health facilities, and as that happened, chances for death decreased, and they come down here toward a line. It would look as though that there were 2 things going on. One, aging changes which we can do something about, and aging changes that we can't do anything about. The changes made by this line, according to this line here today, are changes basically due to an inborn process that we call aging. This curve is such that it starts about age 28 and goes up a straight line. This represents exponential function. In other words, it goes faster and faster and faster with time. Today in Sweden and other developed countries, a group of, say, females born in such a year, a cohort, by only about 1% of that cohort is dead at age 28. All the rest die off in accordance to this curve. And inasmuch as we die off from cancer, cardiovascular disease, and other disorders, this curve indicates that all together they all form this curve here. This is a plot of the chance of death. Incidentally, the chances of death are readily available from vital statistics data. This is the United States population, whole population. It shows it's going up faster and faster. And this indicates why very few of us live beyond 100 years, which is generally accepted maximum lifespan for a man. The maximum lifespan for man is about 122 years, but very, very few people reach past 100 years. The basic problem we have today is that we are near 6 to 9 years short of the potential value, maximum value of average life expectancy at birth. This figure is average life expectancy, a rough measure of a healthy, productive, useful lifespan. And we're gradually approaching that maximum. It underlies the importance of that straight line I indicated. That line represents basically the process that's built into us. There are many theories have been advanced to account for aging, and these are just a few of those which have been advanced. I'm going to talk about the free radical theory. On July 1st, 1954, I joined the Donner Laboratory of Medical Physics at the University of California, Berkeley, as a research associate of Dr. John Lawrence, a physician. He was brother of Ernest Lawrence, a man who won the Nobel Prize for his work on the cyclotron. The day before, I had just completed a superb course in human biology and medicine, 4 years of Stanford Medical School, and a year on a routine internship at the University of San Francisco City and County Hospital in San Francisco. Prior to that time, for almost 15 years, I'd worked in the chemistry laboratories of Shell Development Company, the research arm of Shell Oil. During that period, I received my BS and PhD degrees from the College of Chemistry at the University of California in Berkeley. As an undergraduate, I majored in chemistry and physics and minored in mathematics. When I finished my BS degree, I went to work for an organic chemist, so it gave me an opportunity, a fair amount of opportunity to do organic synthesis. When I completed my PhD degree, which was basically on mechanisms of organic reactions, I switched to the reaction kinetics department at Shell. Most of this work was done on free radical chemistry. And during my 6.5 years in that department, I received 35 United States patents in various aspects of chemistry of free radicals, and also at that time, during that time, developed an interest in biology. This was due to, in part, to the fact I sent compounds to agricultural laboratories in Modesto for evaluation in the agricultural field. And what puzzled me was some compounds which were very effective, others looked chemically almost the same, and yet they were not as very effective. And the question to me was why. During that time also, my interest in biology was further increased by the fact that one night when I came home from work, in the first part of December, my wife called to my attention to an article she had read in a popular magazine, which she thought I might find of interest. I did. The article was titled, "Tomorrow You May Be Younger." It was written by William Lawrence, science editor of the New York Times. And in large part, that was the reason I'm talking to you today. Dear, you want to stand up for a second? You're the person who put me here, so to speak. Okay? You never know until you look back and see what happened. Well, that was what happened. Without that, I don't think I've been doing something else at this point. Now back to Donner Laboratory on July 1st, 1954. My only obligation, definite obligation to the laboratory, was to work in the hematology clinics on Wednesday mornings. Other than that, I could do as I please. On a few occasions, I took off and played tennis. But basically, I settled down to the problem of what causes aging, what can we do about it? I looked at this problem from the premise that there was a basic common cause of aging which could be modified by genetics and the environment. I rapidly became frustrated. Everything I could think of, I let exactly know, whereas I could not account for any one thing that could account for the aging phenomenon that I was acquainted with. And it got progressively worse. It reached a point where I thought, well, maybe we didn't know enough about basic knowledge at that point to make it possible to discern what caused aging. And one morning, in the first part of November, I was sitting at my desk reading, and a phrase, free radicals, crossed my mind. I finally found what I've been looking for. I didn't say eureka, but I just felt a profound sense of relief, having found something. It made sense, both biological and chemical. Next month, in December, I walked around the University of California, Berkeley campus and spoke with a number of people about the possibility that aging could be caused by free radical reactions. The reaction generally was, well, it was a nice idea, but it was too simple to account for aging. Only two people thought that the idea might have some merit. Both were organic chemists. One worked in virology and the other in photosynthesis. It soon became very obvious that the theory would have to be reduced to practice before anybody would pay any attention to it. So almost simultaneously we started working on 4 different areas. One on on catalase, and by analogy to Fenton's reagent, which involved free radicals, another on lifespan studies, another on cancer, and a fourth one on atherosclerosis. During the time that I was at Donner Laboratory, which was 4 years, first 2 years I was full-time, the second 2 years part-time while I completed my work at residency requirements for internal medicine. We published 8 papers in those 4 years, so that by the time this paper in particular received a great deal of publicity, but by the time we left Berkeley to move to Omaha, Nebraska, to take the chair of cardiovascular research, the free radical theory was fairly well known. The theory of the free radical reactions were involved in aging had 2 aspects to it, major aspects. One was that you can decrease the rate of free radical reaction, a decrease in the rate of initiation of the chemical reaction, and or slowing the decrease in the propagation phase with something like antioxidants, you might increase lifespan. This slide is representative of many studies. This is semi-log plot of the chance of death versus age in months. This is for LEF1 mice. This is the control. There's 0.5% and 1% of tumor capital ethylamine in the diet. Nothing else was done. They were started on the diet at about right after weaning, about 3 weeks. This represents almost 30% increase in average life expectancy. But I wanted to call your attention, they all came down to here. By the mid-1960s, enough work had been done based on a pre-radical theory of aging to indicate it was relatively easy to increase average life expectancy at birth in the mice, but no certain increases were observed in maximum lifespan. So the question at that time was, was the theory correct or was it just wrong? I was thinking about this. In several years, in 1972, we published a short paper in the Journal of American Geriatric Society entitled The Biologic Clock, semicolon, mitochondria question mark, in which he asserted that it was a mitochondria that was responsible for our lifespan. I tried at that time to get other people interested in this possibility. I didn't have any more luck on that than I had previously in trying to get people interested in the pre-radical theory of age in the first place. In the 60s and 70s, I stopped by Jaime Miguel's laboratory at NASA in Moffett Hill, California, on my way to a medical meeting. And eventually they published a couple of papers around 1980 and 81 on mitochondria and aging. And I emphasized the potential changes in mitochondrial DNA. Not much happened for a number of years after that. I had to wait the growth of mitochondrial field. In 1989, Tony Linné and his group in Melbourne published a paper in Lancet on mitochondria and aging. And that got wide publicity. And basically, since there's been a growing interest in free radicals and mitochondrial change and aging. This is a study in which we try to answer the question, is there enough changes taking place in the early phases of life, a high metabolic rate and a high mitotic rate that could influence the lifespan? The answer was yes. This is a second study. This is for males. These male offspring of mice whose mothers had been on antioxidants. So males whose mothers have been on these 3 antioxidants produce these curves. The one that tumor capital ethylamine, 0.5% in the diet, increased the average life expectancy of the male offspring by about 15%. The corresponding figure for females is about 8% increase. This was done twice. We expect to see an increase in average life expectancy as a whole. We did not expect to see the effect being a bit greater with the males than with the females. And a possibility is that the females are better protected in the early stages of life from free radical damage than are the males. In early stages of life, females have 2X chromosomes. These chromosomes code for glucose 6-phosphate dehydrogenase, which in turn it keeps NADPH in a reduced form, so it acts like an antioxidant, so to speak. One of the 2X chromosomes is converted to a so-called bar body at the late blastocyst stage of development, just before or about the time of implantation on the uterus. So during this short period of time, it would look as though changes have taken place in the female embryos, it would translate into a difference in effects on age, and also males. And today, there's a lot of work going on in this area, particularly coming out of Europe, where they've found that, and this is now we're talking about humans, where things like hypertension, cardiovascular disease, diabetes, in older individuals can be related back to what happened in the uterus. Gradually, free radical reactions were implicated in a growing number of specific diseases in man. Two major causes of death, atherosclerosis and cancer, and more than that. Many studies have shown mutations in most cases are responsible for cancer. Use antioxidants, you might cut down the rate of mutations and decrease the cancer incidence. In this study here, samples of blood were obtained from about 5,000 women. They were put aside for a number of years. Then they tabulated a number of breast cancers that developed among the women, and also did just serum levels of vitamin E. What they found was that the women whose serum levels had been low at the time the study was started had much higher incidence of breast cancer than higher concentrations of vitamin E. Just a tenth of 3.3, up here 17.5 serum level of milligrams a liter of vitamin E. So low levels of vitamin E predispose you to breast cancer. This is a picture of an aorta of a pig, which is very much like our own. These spots are spots of atherosclerotic change. They're stained with Congo red, and this region seems so easily. Atherosclerosis is a patchy disorder. The areas of involvement are largely determined by areas of injury. In the case of ourselves and in pigs, it is due to mainly due to a hemodynamic force which exerts a suction on the aorta, increasing its permeability, increasing in the subendothelial space compounds from the serum. Some of those compounds are toxic, like possibly peroxides formed by oxidation of polyunsaturated lipids, particularly in the low-density lipoproteins. One might expect to see an inflammatory response set up and development of atherosclerotic lesions. In 1983, there were two studies, epidemiological studies published in the New England Journal of Medicine, one for males and one for females. They both showed that if individuals took 100 milligrams or more of vitamin E per day for at least 2 years, they had a 40% decrease in incidence of cardiovascular disease. This Alzheimer's disease is a growing disorder in this country. It's a function of age. It goes up exponentially after about age 60. About 4 million people have it in this country, and it can strike anyone. Went to service with one for a long time friend of ours last week who died at age 70 of this disorder. A brilliant man, but unfortunately robbed him of his higher functions. This disorder can be divided into several groups we call senile dementia Alzheimer type, the so-called, which represents 90 to 95% of all cases, familial cases, which represent about 5%, and some cases we associate with Down syndrome, starting about age 30, 35 to 40. They would look as though the lesions we see in Alzheimer's disease may be produced at a higher rate in individuals at lower ages. For example, indicate the rate of age in the neurons involved might be faster in Down syndrome than in familial disease and in senile dementia Alzheimer type. I don't have time to go into it, but credible reasons for the increased rate of aging in these various categories. I wanted to save a couple of minutes to talk about the intrinsic aging process, because this is going to be the future. This is what we're going to have to do something about. You can decrease the rate of aging by food restriction, because when you cut down your food intake, you decrease the rate of oxygen utilization, which decreases the rate of superoxide radical production by the mitochondria, so that animals will live longer. We would live longer too. The only problem with that is that you at the same time decrease the production of ATP, our high energy molecules, so after you cut too far down, you become hungry, and after that you feel like you're starving, and you are. So I think it has limited application. About 8 or 9 years ago, there was an article published in the Prestigious National Academy of Science in which the individual's workers had studied the effect of phenylbutyrylnitrone on gerbils. And they found that what they did, they had two groups of gerbils, one young and one old. And before they started their experiment, they number of errors made by the both young and old. And this indicates that old ones made over twice as many errors as young animals. They also found about protein oxides in the brain. Again, it was higher in young and the old and young, and also their relative activities of glutamine synthetase and proteases. When they gave these animals intranasally injections of phenylbutyrylnitrone, the curves, young animals, after over a period of about 2 weeks, all became like the young animals, and when they stopped the phenylbutyrylnitrone, the animals went back to where they were to start with. These compounds of this nature are now being studied intensively. We may see some data in the literature before long, but indicating that you might be able to slow down significantly the intrinsic aging process. Mother Nature has done this. For example, there's a strain of mouse, a white-footed mouse. They live 2 or 3 times as long as the normal mouse, and it seems to be related to the fact that they convert a smaller fraction of the oxygen they utilize to superoxide radicals than the average mouse. There's also been studied in birds and rats, and they find the same thing. The birds have a higher metabolic rate and live longer, in spite of the fact that they have a much higher oxygen consumption. But again, it's a percentage of oxygen that is diverted to free radical makes the difference. Recently, a year or two ago, there was an article in I think it was in Nature, in which a group in Italy made a single mutation in a common gene called P66 superscript SHC. They achieved a 30% increase in average life expectancy of the mice. And no other changes they can detect. It's something like going from the regular mouse to the white-footed mouse. I can't predict the future, but I think the chances of being able to interfere with the intrinsic process and increase our healthy lifespan significantly, I think are very good. In summary, I've talked a little bit about the phenomenon of aging, the basis of how it came, the free radical theory of aging, and also some of the applications of this theory. And also pointed out that the chances are increase in our healthy lifespan are very good based on studies using this theory. Thank you.
Carnosine is a dipeptide that has recently aroused a lot of interest for its various anti-aging properties, mainly due to British, Russian and Australian research. Indeed, in Australia, Carnosine has been voted the anti-aging product of the year, and many believe it is set to become as popular as vitamin E. Here to extrapolate on the clinical trials and his own findings is the founder of the British Longevity Society and one of the few anti-aging physicians in the United Kingdom. Would you please give a warm welcome to Dr. Marios Kyriazis.
Hello. Before I start, I would like to tell you about a strange phenomenon. At the end of the lectures, you are going to be given an assessment questionnaire where you will have to tick the different boxes next to the name of the lecturer. And I find that when I usually ask the audience to tick the very good box next to my name, that they usually do it for some unknown subconscious reason. So I'm asking you now, please tick the very good box next to my name. During the next few minutes, I'm going to go into some more details about carnosine. But I would also take the opportunity to tell you a few general things about the biology of aging in general terms. Carnosine, as we've seen before, is a combination of 2 amino acids, amino acids is a dipeptide. The amino acids are beta-alanine and L-histidine. It is a naturally occurring substance. It is found in the muscle and nervous tissue of all animals, including humans. There are several related compounds and metabolites with similar structure. For example, anserine, carnosine, one which is very famous at the moment, N-alpha-acetylcarnosine, which I'll tell you some more details later on, and other imidazole-containing dipeptides. You can see here the structure of spinosine, which is a similar compound to carnosine. All of these compounds have a range of biological activities, which is more or less similar to that of carnosine. But carnosine is one of the most well-studied of all of these. Carnosine is inactivated by carnosinase, which is an enzyme found in the blood and within the cells, but mainly in the blood. This enzyme breaks the bond between alanine and histidine, producing the two individual amino acids. Once carnosine is able to find its way within the cell, then it's relatively safe from the actions of carnosinase because, as I said, carnosinase is not that active within the cell. So on the face of it, it appears that because carnosinase destroys carnosine, then it must be something bad and we should avoid it. This is the rationale behind the thinking of people who suggest that taking megadoses of carnosine to flood and overcome the carnosinase system, and therefore to increase the amounts of free carnosine in the blood. But there are questions to be asked. Carnosine is much less toxic than histidine. We are talking relatively here. So why does the body want to actively promote the production of a relatively toxic compound, i.e. histidine, from a less toxic one, i.e. carnosine? Alan Hipkiss of the University of London has suggested that it is histidine that has the biological benefits related to carnosine, and not carnosine itself. Carnosine may serve as a reservoir of histidine, and it is used by the body if and when required. Also, why did nature create carnosinase in the first place? There must be some good biological reason which we should try to discover. So the first general point I would like to make is that we shouldn't jump into conclusions about the biological significance of different substances, because nature is much more complicated than we first imagine. There are hidden mechanisms within nature processes which may not appear to us as soon as we start studying something, and we should be careful not to be too simplistic. Now, carnosine has a variety of biological actions. We've seen before in the previous lecture some of these actions. It extends the maximum cell division capacity. We are talking about fibroblasts here. Fibroblasts are cells found in the connective tissue, like the skin. You all know about the Hayflick limit. It's the maximum number of divisions a cell can attain. It's about 50 times in a lifetime. However, carnosine is able to increase this limit to up to 70 times, which is quite substantial. This was proven by McFarlane and co-workers in Australia on 2 or 3 separate occasions. Also, carnosine protects against DNA oxidation, and it is a free radical scavenger. It fights oxidation in 3 fronts. Carnosine fights oxidation in 3 fronts. The first step is that it prevents oxidation from taking place. In other words, it finds free radicals, combines with them, and eliminates them. So the free radicals don't have any chance to cause any damage. But let's say that if this process is overcome and damage is caused, then carnosine protects against the byproducts of oxidation, such as aldehydes, for example. I'll tell you some more in a minute, which aldehydes are damaging to proteins. But say even this step is overcome and damage has already been done, then carnosine helps elimination and repair of already damaged proteins. Apart from all of this, carnosine is a cell membrane stabilizer. It protects and stabilizes the membrane of the cells, and it is a very good intracellular buffer and anti-toxin agent. In other words, it binds with different toxins within the cell and inactivates them. Carbonylation is a process which happens to all of us, whether we like it or not. Carbonyl groups are chemical products which are formed during everyday metabolism. They attach or they modify proteins, causing a lot of damage. Carnosine inhibits the formation of carbonyl groups by, for example, by preventing the formation of substances which cause carbonylation, like aldehyde damage, and thus reduces the formation of abnormal proteins. Glycosylation is another process carnosine takes part in. So we've seen the process of oxidation, free radicals is one. Glycosylation is another. Carnosine blocks glycosylation and reduces ages, and so it prevents cross-linking. Say that my hands are proteins. This is one protein, this is another protein. Proteins have side chains. My thumbs are the side chains. These side chains form like they are receptors for substances to bind onto. So these two proteins, minding their own business, biologically and biochemically, are impossible to bind together. My thumbs cannot come together on their own. So proteins on their own cannot cross-link. However, sugar molecules and aldehydes can go in between my thumbs and facilitate the cross-linking. So a sugar molecule attaches to this thumb and to the other thumb, brings the proteins together. The proteins are cross-linked now. As soon as they are cross-linked, they bend and twist, and they are not good for anything. They have no biological action. Carnosine prevents all of this from happening. Carnosine goes and attaches and protects the side chain like this, and to the other protein like that. The protein is still able to have good biological actions, but they cannot come together. A sugar molecule sees two protein molecules and says, aha, two protein molecules. I'm going to go there and cross-link them. Goes there, the sugar molecule tries to attach to the protein and cannot attach to the protein. Goes to the other protein, cannot attach. After a while, gets fed up and goes away. And the proteins remain free to have their biological actions. It was mentioned before that carnosine can break existing bonds. So if the proteins are already cross-linked, carnosine can break these bonds. I think this is still a matter of debate, although I think it may prove to be correct at some point, because as I would explain in a few minutes, carnosine can reverse age-related cataract damage, which can only be done by breaking existing bonds. Remember that the discovery of carnosine goes back 100 years, and it is only now that it started gaining support as the real elixir of youth. It has been used as a multi-purpose healing agent. Examples are, it was used in joint pains, arthritis, and other rheumatic conditions, in peptic ulcers in high doses to improve peptic ulcers, myopathy, muscle weakness, and other similar muscular conditions. It also promotes healing of wounds and skin trauma, and it has been used extensively in burns to improve burn damage. And it has been used in high doses, again, for radioprotection following radiotherapy in cancer. Can I ask you now, is there anybody in the audience who uses Carnosine? What doses are you using? You don't know? Okay. I won't ask why you're using high doses, but for general anti-aging purposes, Carnosine has been used between 50 and 150 milligrams a day, and like some people here, in 1,000 milligrams or even more a day. I'm talking about anti-aging here, not for specific treatment of specific diseases like radiotherapy damage. There are some side effects related to use of Carnosine, but these are not many. There are some rare cases reported of muscle twitching or stomach upset, like nausea. In fact, the actual preparations of Carnosine, it comes in 50 milligram, 100 milligram, and 500 milligram capsules. It is soon to be marketed in eye drops. We are all waiting for Phil to let us know when. I think he's saying at the end of August. And it is also available in skin form for skin improvement of skin, age-related skin damage. It can be used together with any other anti-aging supplement or drug, but particularly coenzyme Q10, vitamin E, and DHEA, as well as Lucidril or similar substances. Other potential uses of Carnosine, because it prevents glycosylation, it is useful in reducing diabetic complications like kidney or vascular damage. It can prevent or protect against liver damage, such as alcohol-related damage, exactly because of it is a good aldehyde protector. And it is used as a cancer preventer and in treatment in high doses. Because it reduces the formation of beta amyloid and senile plaques, it may be useful in Alzheimer's dementia as well, but more research is needed in this area. Coming back to the use of Carnosine eye drops, there are two main researchers who examine this area. One is Dr. Wang from Harbin University in China. He studied 96 patients, age 60 and above. Dr. Babisayev from Russia also did quite a lot of research, and he's involved with marketing the Carnosine drops. He studied in his latest experiment 49 patients with N-alpha acetylcarnosine, which is a particular configuration of carnosine, thought to be more effective and less susceptible to destruction. He found that initially there was a 41% protection improvement in light transmission through the lens, whereas a total of 90% of people reported a gradual improvement in visual acuity. This is supposed to be a man fighting Father Time. That's what we are all doing here. And we can do this with Carnosine, among other things. Carnosine, in my own experience, using it in patients, it can improve mental and physical well-being. It can improve muscle tone, particularly the muscles of the face, people report that after using Carnosine for a month or two, their face looks firmer, their muscles in the face look firmer, and this gives them a naturally younger appearance. It can increase hair growth in those who have thin or fragile hair. And in some rare cases, people have also reported an improvement of the sense of smell, sleep patterns, and sexual enjoyment, which has been predicted by theory. Carnosine is supposed to help the olfactory nerve recover after damage. I did a small trial to find out what is the best dose of Carnosine. I used a free radical test kit, which is available outside in the exhibition area. During the break, you are going to get a little photocopy of the details. This test kit checks MDA, malondialdehyde, which is produced after following lipid peroxidation, damage of free radicals to the cell membrane. So MDA is a toxic product which we should all try to reduce. Carnosine is believed to protect against this, and I thought I'll use Carnosine in different dosages to see whether it has any impact on the urine of patients at home, not hospitals or laboratories, ordinary people using Carnosine at home. I studied it on 12 healthy volunteers, aged 40 to 75, and I used different doses of Carnosine, starting from 50 milligrams, 100 milligrams, 2, 5, and 1,000 milligrams, 200, 500, and 1,000 milligrams a day. My results are so hot that I couldn't even have the time to put them on the computer. Somebody's trying to take the photocopies quickly now. I only got this recently. And I found that the ideal dose of Carnosine is between 100 and 200 milligrams a day. You'll probably see later on that using 500 or 1,000 milligrams a day hasn't got any additional benefit to lower doses. And the assertion that at least 1,000 milligrams of carnosine are needed in order to overcome the carnosinase destruction system. How many? One a day. So this assertion that we need to take at least 1,000 milligrams to bypass the carnosinase doesn't hold true, because I've seen results with even 50 milligrams a day. So 50 milligrams a day does something to the body, it's not inactivated. So to conclude, carnosine is an all-round anti-aging product. It is very easily available, and it's thought to be natural because it's naturally occurring in our body. It can be used with other treatments, particularly Q10 and vitamin E, and there is quite a lot of research supporting it. Statistics show that after a presentation like mine, the audience only remembers about 10%, if that, of what it has been said. So whatever I have been saying for the past 20 minutes will probably go wasted. So if you have to remember something, I would like you to consider this. This is an allegedly 140-year-old man living in China, recently discovered by a British newspaper. This brings me back to an earlier point that you shouldn't always believe what you read, or if you read any stories in the media. So if you look or feel like him, and you take your daily carnosine, then you may help reverse aging and end up looking young and healthy again, like this young man here. Thank you.